Okay, so we're going to use picture patterns, looking at this pattern of marshmallows and toothpicks, making cubes, to come up with a relation. So a relation, obviously the word means relating things together. So relating the number of cubes to the number of toothpicks, number of cubes to the number of marshmallows. So 3 of them are done. You've done the 4th one for 4 cubes. Okay, so there is a relation between the number of marshmallows and the number of cubes. In this situation, the number of marshmallows is dependent on the number of cubes we're making. We have to know how many cubes we're making before we know how many marshmallows we need. So folks, I need your phones to be away, please. Therefore, we say the number of marshmallows is the dependent variable. And what it depends on, the number of cubes, is the independent variable. Okay. So the relation between the number of marshmallows and the number of cubes can be represented as a table of values. In a table of values, the independent variable is always in the first column, and the dependent variable is always in the second. Sometimes we might have a chart that's horizontal just to save space. And so typically the independent is in the first row and dependent is in the second, because you need to know the first value to figure out the second one. And so here we've got the number of cubes. Independent is in the first column, number of marshmallows M. Use the diagram to complete the first 4 rows. And then we'll see if there's a pattern, right? So for cube 1, how many marshmallows? Well, there's 4 in the front, 4 in the back. So there's 8. Count them up. In 2, those stay the same, and we just add on the second cube, but that only adds on 4 more marshmallows, right? The outside edge. So that's going to be 12. Then here, we just add on these, right? Because the other marshmallows were already there in the previous diagram. So that's going to be 16. And then we add on these marshmallows. That's going to be 20. So what's happening each time we add a cube? How many marshmallows? Yeah, you're adding 4. So this will be 24 for 5 cubes, 28 for 6 cubes. Phones away, guys. Tolu. Sit up, please. Don't even know I'm calling your name. Okay, the relationship between the number of marshmallows and the number of cubes can also be represented as a set of ordered pairs. And each ordered pair, the first element is always the independent and the second is always the dependent. They are enclosed in a set of brackets. I call them squiggly brackets. And you might think, oh, I don't care. It matters. Okay, you have to have the right types of brackets. So the squiggly brackets is the set of all the ordered pairs in this case. So we continue here. This will be 316 in round brackets, comma, 420 in round brackets, comma. I'll do one more to fit it in, 524 round brackets. And then this could go on forever, right? We could have, keep adding squares, or cubes, I should say, onto that diagram to infinity. So if that pattern continues, then we use a comma with 3 dots. It means that pattern continues forever. Okay. The domain are the values that are the independent values, the first values. So 1, 2, 3, 4, 5, 6, and goes on to infinity. Right? So those are the independent values is domain. So you have to memorize that. Okay, so independent values. Often, if it's just any kind of relation, it's the x values. So usually in any relation that doesn't have an application, it's x and y values. X is the domain, that's y is the range. Think of alphabetical order. X comes before y in the alphabet. Domain comes before range in the alphabet. Okay, so that's domain, and then the range, we use capital D, capital R, squiggly brackets, and what is the range? Our first value was 8, then 12, then 16, then 20, 24, 28, and on to infinity. Okay, following that pattern. Oh, what did I just do? Okay, so that's showing the relation as a set of ordered pairs, talking about the domain and the range, and then showing it as an arrow diagram. So in an arrow diagram, this is always your domain, and it needs to be in a circle or a oval shape, and this is always your range. Okay, D comes before R, X comes before Y. Okay, so that often helps. And so take a look from each domain value, the number of cubes, the range has an arrow towards it. So then for 4 cubes, it was 20 marshmallows. For 5, it was 24. Now in this case, our circles are kind of close. So really in our chart, I'll go to 6 because that's what we went to in our chart. It's hard to show infinity in an arrow diagram, but you could put the dots underneath, although we rarely do. We usually do it for a small set, the arrow diagrams, okay? And usually we write the values in order. So sometimes the arrows might overlap. They might crisscross depending on what their range value is. In this case, they're both increasing. So that's an arrow diagram. So turn over the page. Oh, sorry, is it turning over the page yet? Sorry, my thing is so messed up. Yeah, turning over the page to the graph somewhere. Did I lose it? What's up? Yeah, sign out. Okay, looks like I lost a page, so just give me a sec here. I'm going to insert number 8, the relation between the number of marshmallows and the number of cubes. So we can represent it by a graph. Dependent is on the vertical. So this is the number of marshmallows. So you can probably do that easier than me. So this number of marshmallows, this is the number of cubes. Okay, so for 1 cube, remember it was 8. 2 cubes, 2 cube had 12, 3 cubed has 16, 4 of them had 20, 5 of them had 24, 6 of them had 28, and so the pattern would continue. Label the axes, which we did. You must have, now here I would also label the number of cubes. If you look back in our chart, we use the variable C, and then marshmallows we used M. So this I would put a little C there, this I'd put a little M, but then label with words, okay? Reminder that you must have even spacing between your little tick marks, your grid marks, and go up by equal amounts for each. The scale on the 2 axes doesn't have to be the same. Notice how here 1 grid marking is 1 unit, but vertically 1 grid marking is 4, right? So it just has to be equally spaced. So take a look at those. Do they form a straight line if you were to get a ruler out? Yes. So we're going to spend a lot of time talking about linear relations. If those points all lie on a line, then it's a linear relation. And yeah, so we'll get to that in a few days. But right now, whether we join them up is important. So should I join those points up with a straight line? Yes, they would lie on a straight line. But if I draw a straight line, does that make sense for the number of cubes and the number of marshmallows? No, why not? Right. You can't really have half a cube. Then it's not a cube, right? Ken, did you have your hand up? It's discrete. Good. You know the language. Yes, it's discrete. So if you can't have part of an item that's represented by this, then you don't join them up. You might join them up just to extend it further to find some values, just to make it easier to read. But technically, these ones should not be joined up. Ones that typically are is if our independent is time, because time goes on forever. You can't jump from 1 minute to the second minute without the in-between parts. So anything to do with time is typically continuous, but in this case, these are objects. You can't have half a cube. Then it's not really a cube, right? So you probably noticed that the points he plotted all lie on a line. Should you connect the points with a line? By connecting the points, this means that every point, including the ones between them, makes sense for the situation. Note that the line passes through the point 1.510, which means that you can make 1.5 cubes with 10 marshmallows. Does this make sense? No. Should they be connected? No. Right? You can't have half a cube because then it's not a cube. So if it makes sense for the points to be connected, we say that the data is continuous. If it does not make sense, we say it's discrete. In this situation, the data is discrete. And therefore, the points should or should not be connected. Should not be connected. Okay, examine the values in the second column of the table. You may have noticed that the pattern in the second column of values is to add 4 to the previous. What if you wanted to determine how many marshmallows are needed to make 56 cubes? One way to determine the answer is to keep adding 4 until you get to the 56th row. But you probably don't want to do that. And that's okay, just hold on a sec. Probably don't want to do that. That would take you a long time. Instead, it might be better to find a rule that relates the number of marshmallows to the number of cubes. Examine examine each row of the table to find a rule. Check to see that the rule works. Write it by completing the following statement. So, Seth, what did you say? Okay, so let's go back to, in terms of words, 4 times what did you say x would be then? Right. So take the number of cubes and multiply by 4. And then what do we do, Seth? Right. Okay, multiply by 4 and then add 8. Now, does that make sense though? Let's check. If we start with 4 and add 8, we would get 12. So we've got to think again about the first number. Or sorry, what we add here. So, oh, did I lose that page again? Here it is. Okay, so if we take 1 cube and multiply by 4, we get 4, and we're supposed to have 8 marshmallows. So what do you think we should add? 4. So we add 4. Let's check it with the second cube, 2 cubes. If we take 2 times 4 is 8. We're supposed to have 12 marshmallows. 8 plus 4, is that 12? Yeah. Good. So that's our rule. So now here, if we want the number of marshmallows, we're going to have 4 times the number of cubes plus 4. That's our equation that represents this relation with those variables. Okay, so now if we want 56 cubes, we're going to substitute 56 in and evaluate that. Do it without a calculator. Okay. Just in your head. But I don't think it's 128. Okay. Yeah. Okay, so because 4 times 50 is 200, 4 times 6 is 24, plus 4 is 428. Okay. Oh, sorry, 228. Now I'm getting all messed up. 1, 2, 4, 228. Okay. So your equation, so we can work backwards as well. So say we knew we had a certain number of marshmallows, then we could work backwards to know how many cubes. So it says here, use your equation to determine the number of cubes that can be made with 460 marshmallows. So that's your M. You put that into the equation, right? And you solve for C. So this is back to junior high solving. So you subtract 4 from both sides. So that's 456. Then you divide by 4 both sides. So C equals 100 and goes in once 114. Okay, so if you have 460 marshmallows, you can make exactly 114 cubes joined together like that. Okay, so those are relations shown by set of ordered pairs, shown by an arrow diagram, shown by a graph, shown by an equation. The equation is the easiest way to find missing values. Okay, so you try this one. Look at the relation between the number of toothpicks and the number of cubes. So go back to the first diagram and fill in how many toothpicks. Okay, so if you don't have your notes, there's the diagram. So count them up. First one has 4, 8, 12 toothpicks. Okay, the front and the back and all the ones on the side. So this has 12 toothpicks. Then if you're adding on, you're adding 1, 2, 3, 4, 5, 6, 7, 8. So this has 20 toothpicks. Okay. So you fill in that chart based on that diagram. Relation as a table of values. So as a set of ordered pairs, you need the squiggly brackets, round brackets for each set. I'm going to stop there just because I have to write really big because something happened to my stylus again. But that pattern could go on forever. So just make sure you have the dot, dot, dot. So for the domain, it's capital D, a colon, squiggly bracket, and then just the domain values, the number of cubes. Okay. So really those in this situation are the set of natural numbers, 1 to infinity. Range, 12, 20, 28, 36, 44. Well, I guess I could do 52. I can fit it in. Dot, dot, dot. Close the brackets. As an arrow diagram, okay, you got to write a little bit small. So you have your one oval, your other one, and then 1, 2, 3, 4, 5, 6 will fit in what was in our chart. This I'll have a little bit harder time with my stylus isn't working. Not bad. And then an arrow across to each one. Okay. Obviously that could continue forever, but with an arrow diagram, we'll keep it to that particular table of values. And then graphically, so this is the number of cubes. Okay. And then this is the number of toothpicks. Okay. And then what was it? It was 1. So take a look here. We started at 12, right? So 1 was 12. 2 was 20. 3 was 28. It's hard to me to make a dot, nice dot. But they're going, each grid mark is going up by 4s like the last one. But ours, each increase of a cube, it's going up by 8 for the dependent. So then this will be 2 grid markings higher, 2 grid markings higher, 2 higher. Okay. So my dots aren't very good just because I don't have my stylus, but it is forming a straight line. So now in this case, you could even, if you drew a straight line through this, I'll maybe do that and then I can erase it. If I draw, I'll do it in red. If I draw a line that goes okay, so now I'll just fix that a little bit, move it so it's okay. Now that's not even working. There we go. Okay, that's going straight through. Okay, you can tell how many toothpicks, sorry, not how many toothpicks, but basically what the constant term in that equation will be. Where it crosses on the vertical axis, it crosses at 4. So that means when we write our equation, or this will be in words, determine the number of toothpicks needed, take the number of cubes and multiply by 8. And add 4. Okay, so if I go 1 times 8 is 8 plus 4 is 12. That's my first value. 2 times 8 is 16 plus 4 is 20. That's my second value. That line there, I'm not joining it up to represent the actual, there we go. I just put that there so you can see where it crosses because these are discrete values. That red is extra as well. Okay, but that will be your formula. So we're going to use variable t for toothpicks. So t equals 8c plus 4. 8 times the number of cubes plus 4. So now how many toothpicks for 36 cubes? Well, 8 times 36 plus 4. Okay. Okay, Miles? Yep. 292. Yep, looks about right. 292, because 8 times 30 is 240, 8 times 6 is 48, and plus the 4, so 292. Then working backwards, if you have 1964 toothpicks, that's a lot, how many cubes would be in your diagram? So remember back to junior high, you're going to subtract 4 from both sides. So 1960 equals 8c. Then we're going to divide by 8. So that goes in twice, 220, right? 245, what did I do wrong? I'm not using, okay, let me do this again. No, it's Friday. 2 goes into that. sorry, 8 goes into that twice is 16, right? 36, so it goes in 4 times. 4 goes in 5 times, right? I was thinking 9, dividing by 9. So that will make 245 cubes. Obviously, if you didn't have an equation, you'd have to make all 245. That would not be fun, right? So that's why equations are useful for you. So turn over to the last page before the practice. Just a summary there, all the different ways that we can describe a relation. We've gone through those. Here's a new scenario. A used bookstore charges a one-time membership fee of $45, then $5 for every book you buy. So, table of values. So if you sign up, this is saying that for 0 books, it's still going to cost you $45 just to be a member. Yes. Yeah, quickly. So then for 1 book, it will be a $5 extra to that. So that would be $50. For 2 books, your total charge would be $55. So this is a different scenario. It's not going to then cost another $50. It's a one-time fee of $45, and then for each book, it's $5. Right? So obviously your amount is going up 5 each time. So you can fill that in as a set of ordered pairs. I'm just going to start it for you. Okay, so at least have 3 ordered pairs so you can see the pattern. Arrow diagram. That one wider. So that's 0, 1, 2, 3, 4. I'll go to 5 and fill that in. Then 45, 50, 55, 60, 65, 70. Arrows go across. Obviously, that can go on forever. Okay. Graph, you can graph it. We'll just do the equation. Okay, so here, who can tell me what the equation would be? Who thinks they know? Seth?
$1 would be 5. The cost of 5 is.
So cost equals
5 plus.
Good. Yep, $5 for every book, and their $45 fee just to open the membership. Okay. Okay, I'll leave the graph for you to do. Do you think it's discrete or continuous? Can you have half of a book?
No.
No, it's discrete. Okay. Okay, so if you have a graphing calculator, let's graph this. One last thing here.
That's why she's going to show you.
Okay, so in a TI, you go to y equals, and you enter. So that was 5x. The x key is next to the alpha key. It's selected red there. And then plus 45. So take a look. Make sure the plot 1, plot 2, plot 3 aren't selected, because that means something else is graphing and it might conflict. Make sure there's no other equations there. Amy? Sit up, please. okay? And so then if I were to graph this right now, what I suggest you start with is, I always start with a standard window. So go to zoom and number 6, so cursor down. And then again, this is for TIs. I'll show you the Casios in a sec. Enter on that. And you can only see part of the line because standard window goes from -10 to +10, both ways. Can you buy a negative number of books? No. Can you have charge you negative? No. So really in our window, yeah, you could, but so then 0, let's go to like 20 books. So go to window key, 0 for X min, 20 for X max, go up by scale of 1, then 0 for Y min, and then obviously more than $45, that's your base amount. So let's go to like $200. And now press graph, and now you can see the graph, and you can see the X and Y axis there. Okay, so now if you press trace key, it will go to one particular point on the graph. But if you punch in an X value, so if I want to know how much it would cost for the membership and 12 books, then I punch in 12, it goes into the X value, I enter, and it goes and it tells me $105. Okay. So now if, let me get my Casio out, menu, so make sure you see your menu there, and go to graph. So cursor down on mine, yours might be in a different position, and then execute on that. And so I have some graphs already in there. I'm going to delete the formula, F1, yep, cursor down. So delete anything that might be there. Probably you don't have anything yet. Okay, go back to Y1 and then do the same thing, 5, and your variable key is over, it's called X, theta, and T, so it's over here for mine, and then plus 45, enter, or cursor down out of that, oh, can you do that? Yeah, execute so that your line is down below. If it's still on the graph, it won't do it. Now go to, see an F3 where it has V window. That means I've got to go Shift F3 to the window, and I'm going to make that 0 for X min, 20 for X max. Oh. Okay, arrow down. Don't worry about the dots. 0, max 200. Okay, and then graph it. So, we'll exit out of that. And then in this, keep watching, is draw. So you do F6 to draw it, and there it is, same thing. Okay, within the Casio, if you want to find a certain point for a certain X value, go to trace, so Shift F1, and then you can go along. You'll notice that they're all decimal values, but if you press, so if I want to find when X is 12, as soon as I press a number, they understand, the calculator, just like the TI, that X is 12, and then execute on that, and it goes right to it, 105. Okay, so both calculators can do the same things.